Hey everyone, in this section we're going to expand our ability to be able to use integrals and now apply it in the realm of finding volumes. So to help us understand where we're headed with things, we need to think about where we've been already in terms of using integrals, and mostly what we've used integrals in a lot of different contexts has been being able to find the area of certain regions. So if we think about what our definition has been for being able to find area in a curve, remember that when we're trying to find area, what we really did to be able to kind of approximate is we did like a Riemann sum type of a technique, right? Where we would break up our region into rectangles and then find the areas of these rectangles and ultimately make the rectangles be so infinitesimally small that ultimately we'd converge on what the actual area is in this particular curve, right? So really what we defined that to be is if we said that the width of each of these rectangles was kind of the change in each x, the I is just denoting which interval it is, the ith interval. So like this right here would be the I minus one interval, or the next interval higher would be just the I plus one interval, right? So basically just the change in x right there. And then the height of each interval would be like f of x sub I, some determining factor to determine the height. Then basically each rectangle would have an area of its width, so the change in x, and then also the height, which would be f of x sub I star. And then we would just add up all those rectangles. So we'd add them all up from the first rectangle up until the nth rectangle, right? So we want to make it so that there's an infinite number of rectangles. So when we then limited, and we went let n go to infinity, then this was our definition for the definite integral, where then the integral from a to b would actually be the area under the curve, right? So that was what we've dealt with and seen so far. So it turns out that we can just kind of generalize this idea to be able to find volumes in three-dimensional space rather than the two-dimensional space calculus that we've done really for the entirety of this semester so far, right? So, an easy way and an easy analogy to help you understand what we're about to be doing here is to just think of the fact that we're going to be slicing up our region, our three-dimensional region that we're going to try to find the volume of, slice it up and add up all the slices. So like you see in the picture right here, you just see like a 3D region, which is like a loaf of bread, right? But we want to take that loaf of bread and slice it up into different slices. And what you'll find then is that each slice of bread is going to have a little bit of thickness to it. So it's going to have some sort of a change in x. But then what we're going to want to multiply that by is, instead of like here where we were trying to find area, where this right here was going to be a height, we actually want to multiply each change in x with what the actual area of each slice is. So we actually want to take like the area function at each ith interval and then multiply it by the change in each x. So kind of the width of each slice of bread. So this is just the width of each slice, right? And this is just the area of each slice. And then if we basically just kind of do a Riemann sum type of a thing, this will ultimately lead us to how we can find the volume here. Okay, so we're going to formalize this in just a little bit, but that's just kind of the general idea of what we're basically going to be doing. And you're going to see this, how this slicing bread analogy carries over in our first initial examples that we'll work through. Okay, so just some terminology of the different figures and shapes and stuff that we're going to be working with. So this right here, to no surprise to anybody, is of course a cylinder. So when we define what a cylinder is in geometry back in middle school and high school and such, we just define it as a shape that has a circle on both the top and the bottom. So the terminology that we want to relate to the calculus that we're going to be doing is to call these circles here the bases, where basically the bases are going to be parallel or in parallel planes to one another. and then they're just separated by some distance between them, right? So they're separated by the height of the cylinder, right? So we want to generalize that definition of a cylinder, because then when we generalize that, we can start talking about any sort of three-dimensional shape that might have bases that are the same on both the top and the bottom. So what you're seeing in the pictures here are actually things that we could say are also cylinders, but just more generalized cylinders, where you can see that this shape has both the same top and bottom shape, and then you just fill in the space everywhere between those parallel bases, right? And even the shape that you're seeing down at the bottom there, so this shape down here, also has the same base at the bottom and top. Now, it's got like a slanted height, but that's okay for our purposes to be able to talk about a generalized cylinder. So that's what we mean when we have a generalized cylinder. So it's just basically, just like a 3D shape with with two bases that are in parallel planes to one another. So they just have some sort of a height distance ultimately separating them, right? So that's what we'll refer to as a generalized cylinder, and a lot of the types of figures that we're going to try to find volumes for, what we're going to really do is we're just going to slice each of these up, and so we'll try to like find like kind of the approximate volume of a slice, and then another slice and another slice, and use that sort of setup to be able to set up some integrals here today. Okay, so we haven't done any like calculus yet, but just helping you see some pictures and put some definitions to things that we're going to be doing. So this is right here now kind of the motivation for how we're going to try to integrate here. So what we're going to try to do is we're going to basically try to talk about how we can find the volume of this region. And when I say this region, this whole blue figure. And so the method that we're going to use to begin with is going to be called the slicing method. And basically what that means is you're just going to take slices like a loaf of bread, but you want your slices to be parallel to the bases of your generalized cylinder. So what I mean by that is you should recognize that this base right here and this base right here that I've now colored in the gray color, they're parallel bases in this generalized cylinder. And so when we're slicing like our little pieces of bread, we're making slices that are going parallel to the bases, and each slice, if we keep adding more slices throughout, is going to kind of move its way through the entirety of the prism, right? So we're basically just going to want to try to add up the volumes of each of those slices. So each of these slices are going to have a width that's going to be a change in x, which basically is happening between these intervals from a to b. So what we're going to be ending up doing here is as we transcend over this interval from a to b, we're going to integrate from a to b, so basically the starting number of the base of this cylinder all the way to the ending number of the base of this cylinder. So what we need to integrate as a function, though, is we need to integrate using what the area of each slice is. So like if you looked at the front of your slice of bread, like what would be the area function for that? So we're going to integrate the area function of that. And then also we need this change of x. So multiply by change of x, which is really equivalent to dx. We also need the dx when we integrate. So this is really what we're going to try to do from a to b. And then that's going to equal the volume. So really, volume is just integrating area, really, if we kind of generally speak about it in that way. We'll now get into the very specific examples where we're actually going to now find volumes of certain regions. And where we'll begin is by using this method of slicing, and later on we'll transcend into other different methods that we can find volumes of three-dimensional regions. So what we're going to start with for some of these initial examples is some figures that are common solids that you are familiar with from your K through 12 math experience. So the first thing that we're going to look at right here is just finding the volume V of the sphere that has any given radius r. And we'll use calculus to be able to find this. And so the first thing that I want to start with right here is just recognizing and acknowledging how in the world are we going to do this. And how we're going to do this is we're going to do this by slicing this. Just like taking a loaf of bread, and if you put all the slices of bread together, you get the entire loaf, right? So that's what we're going to do right here. So what we're going to need to do is we're going to need to figure out what our cross-section shape is going to be that we can like add together all the way throughout the entirety of the volume of the sphere so that it shows up to be the volume of the sphere. So what we're going to do is we're going to, along the x-axis, add up a bunch of circular cross-sections. So what that would kind of look like is, for example, this circular cross-section right here of the sphere would be something that we would add with a bunch of other circular cross-sections. So for example, like this circular cross-section right here, or this circular cross-section, but they're all going to move along the x-axis. So basically we're just going to add a bunch of circles that starts here and ends right here. So if we do really truly think about the sphere being oriented in the three-dimensional XYZ Cartesian plane like this, we can think that it's really centered at the ordered triple 0, 0, 0 right there. And so what we'll do is we're actually going to integrate then along the x-axis. So basically from whatever number this is to whatever number this is. Now, just because a sphere is symmetric and stuff, and for simplicity's sake, if we actually only integrate from 0 until we get to that number, that's actually going to be finding the volume of half of the sphere. So that's actually what we're going to do, is we're going to integrate from 0 to whatever that number is right here, which is actually going to be r, because this would be the radius r right there. And our spheres of radius r. So we're going to integrate from 0 to r, but then we're just going to double that integral, so we double the volume, and that's going to be the volume of our sphere. So what we need to integrate is we need to integrate the area of each of these cross-sections that we're sliding along the axis between 0 to r, sliding along the x-axis. So what I need to figure out is, for this circular cross-section right here, what is the area of that circular cross-section? So it's just going to be a perfect circle, and we know that area is equal to pi times the radius squared, right? So what we need to figure out, though, is we need to figure out what the radius of that circular cross-section is. So what this distance is right here, what that particular radius is. We need to get it as a function of x as well, because since we're sliding along the x-axis, our integral is going to have to be integrated with respect to x, since that's the corresponding to what these limit numbers are along the x-axis. So we need to figure out a way to get a function of x to determine what that blue radius r is. So what we could do is we could actually use the Pythagorean theorem to determine that, because this diagonal distance from the origin out towards the edge of the sphere is actually what the actual legitimate radius of the sphere is. So this radius is the same thing as this radius. And then this distance down here is actually x, how far you've moved along the x-axis. So that means then that this distance right here, just by the Pythagorean theorem, would be the square root of that hypotenuse of r squared minus x squared. Right there. Beautiful. So that's what we would want to use for that particular r, for the radius of the cross-section. So then what we're going to put in here is we're going to put in pi, and then that radius of the square root of r squared minus x squared, all squared, and then we'll integrate this. Great. The pi can come in front because it's just a constant, so you'll have 2 pi, and then we'll integrate from 0 to r, and then if you square the square root, you just get r squared minus x squared dx, and then we can integrate. So we're going to get 2 pi, And then if we integrate r squared, but then it's with respect to x, a different variable, the integral of that is just going to be r squared x, because r squared, we can just treat it like a constant. And then if we integrate x squared with respect to x, then we'll use power rule. It'll become x to the third divided by 3, so 1/3 x to the third. And then we're going to evaluate that between 0 to r. So we'll have 2 pi. It's going to multiply to everything. And we're going to plug in r for x first. And then subtract away and plug in 0 for x. Great. So everything that's happening right there is just 0. So this right here is going to be r cubed minus 1/3 r cubed. And 1 minus 1/3 is 2/3. So you get 2 pi in front multiplied with 2/3 r cubed. And then if you do 2 times 2/3, you get an answer then of 4/3 pi r cubed. That you should remember from geometry. Here in this example, we'll look at another common solid, of which is a pyramid that has a square base. That's why it's called a square pyramid. And we'll want to determine the volume V of this square pyramid. So similar to what we saw in finding the volume for the sphere, we also will use a slicing method, in which we'll basically slice a bunch of pieces of bread that will stack all together parallel to each other, and it'll fill up the volume of the pyramid. So the easiest way for us to do that is to make slices that go parallel to the bottom of our pyramid or to the base of the pyramid. So if we cut through our pyramid parallel to the base, so we make a slice that goes through our pyramid this way, they're all also going to be squares, right? But just smaller squares in the base. And we're just going to want to then take all these thin little slices and add up the volumes of all of these thin slices that run through the pyramid, and that's going to give us the volume of our pyramid, right? So with that in mind then, because we're going to basically take a bunch of slices that will look like this, we're going to run them this direction, so through the height of our pyramid. What we're going to want to do then is maybe express our integral in terms of y. If we think about this axis right here as sort of kind of being like a y-axis, sort of like a height. And we'll want to integrate then from whatever number this lower number is on the y-axis up to what this higher number is on the y-axis. So we might say that this is like 0, and this is h, the height of the pyramid, right? So we'll integrate from 0 to h then in this pyramid. So what we then just need to do is then we need to just get an area of the cross section right there, because then that area function is what we're going to want to integrate since we're doing this with respect to y. But if we say that like this square cross section has dimension x by x, then it's a function of x, but we want to try to get area as a function of y instead of as a function of x. So we need to try to devise some sort of way using some, geometric relationships that we would know about triangles and other sorts of things that can get it in terms of y. And so I think one easy way for us to do that is to kind of look at just a two-dimensional cross-section of this pyramid, like this, and recognize that if this right here is your square cross-section, it has a dimension of x, right? Now, if we say that perhaps, like, the base of this pyramid right here, let's say that it has a dimension of, like s or something, right? Those two lengths right there should be proportional to what this distance right here is of h, the overall height. So, like, the ratio of s, the overall base, with the height should be equivalent to the ratio of x to then just this height right here, which we might just be able to call y. And so then with that, we should actually be able to find some sort of expression that solves for x in terms of y. So by the cross product property, we would know that x times h equals s times y. And then solving for x would equal s over h times y. So we can kind of treat s and h right there as just known constants or numbers, and then y is the variable. So if that's what x is, then the area of this cross-section is really x times x, which would be s over h y squared. So that would be the function then that we would want to use. So s over h y squared would be the area of each cross-section, and then this integral right here would be the integral that we can then integrate to find the volume that's the volume of the pyramid. So simplifying that integrand right there, you're going to have s squared and h squared that you can pull in front because they're just constants. They're different from the y variable that we're integrating with respect to. And then you're just integrating from 0 to h of y squared dy. And then using power rule, it's 1/3 y cubed that will evaluate between 0 and h and multiply by s squared over h squared in front of that. So this would be equivalent to s squared over h squared, and then plugging in h, 1/3 h cubed, plugging in 0, 1/3 0 cubed, which just results in s squared over h squared times 1/3 h cubed. And then you're going to get some h's to cancel. You'll get all the two h's to cancel with two of those. So you're left with just one h. So it ends up equaling 1/3 s squared times h should be the volume then of your pyramid. And that should make sense because we know that from geometry that if you find the area of your base, which is going to be s times s, that's where the s squared is coming from, then you multiply it by the height, and then also by 1/3 because it's a pyramid, that's the volume of your pyramid. So it just verifies what you've already seen in geometry, but just gives us some calculus perspective to the same problem there. Here you just see exemplified just like another way, another setup of how you could find the same volume of the square pyramid that we just worked through. Really, all that's different in this setup is that it's oriented along the x-axis. So the height of the pyramid is oriented along the x-axis, whereas when I worked through it, I said that was the y-axis, right? So it doesn't really matter the particulars and the mechanics of things. Those tiny details don't really matter, right? The big idea in the integration is that the volume is just the sum of its parts, right? And so the idea still persists in this method that we're still using slices of cross sections and adding them up, but this time we're going along the x-axis. And so what that means in the integral then is that you're doing this with respect to x, and therefore your area function for the cross-section, the area of each cross-section, is also going to be a function of x. But I'll echo again what I just stated to you, is that the idea of the slicing method is really just to add up all of the parts, all of the slices together to form your full loaf of bread, so to speak, right? So if you work your way through, the similar triangle stuff that you're seeing here and how the integration work is going through right there, that might be helpful for you just to make some connections and see the similarities and differences between the way that we worked through it in the previous example and how it can also be done in this particular manner. In this example, this will be the last time in which I'll explicitly illustrate how we could use the slicing method to be able to find the volume of a three-dimensional region. In this particular scenario, as you can see in the left figure, there's a cylinder, and then as it reads, we're going to create a wedge by slicing at a 45-degree angle from the cylinder, which has a radius of 2 units, as is shown. And then we want to find the volume of that wedge. And the wedge, you can see, is kind of drawn out separately over to the right. So the way that we're going to go about doing this here is we're going to use already what's shown as that green little rectangle as our cross section, and then we're just going to move those rectangles along this x-axis right here. So for example, if we moved it to here, it would have a smaller width but a taller height as it moved into that part of the wedge, right? So we're just going to try to like add up that volumes of these tiny little thin slices as we progress through. So therefore, in order to find the volume of this, we're going to need to integrate with respect to x and then find our limits that move along the x-axis. So we're really going to be integrating along here from this a number to this b number. So if we actually just think about this, this cylinder maybe actually kind of having like the origin right there, we could think about this number as being 0. And then because we know the radius of the cylinder is 2, then this black distance is actually the radius. So then that means the coordinate along the x-axis right there is 2. So we're going to be able to integrate from 0 to 2 then as we move those cross sections between 0 to 2 then. So what our integrand here needs to be then is this just needs to be the area of each of your cross sections. And our cross sections are just going to be rectangles, I guess, right? So we need to figure out a way then to be able to get the length of each rectangle and then also the height of each rectangle. Now what you'll need to recognize with this here though is that those distances kind of do change, like they're not fixed and constant, because as we moved a cross section right here, the width of that rectangle is much smaller, but now the height has changed quite drastically. Okay, so talking about what this distance right here is going to be, you should recognize that that distance right there is always a distance that's being squeezed between the x-axis and the circle, right? So what you should recognize about a circle like that, that's centered at the origin, is that has an equation where x squared plus y squared is equal to the radius squared. Now in our case, because the radius of the cylinder is 2, then the radius of this circle is also 2, so it should equal 4, because that's 2 squared. And then we could actually solve that circle equation to be a function of x, because this would be equivalent to y equals the square root of 4 minus x squared, once you go through the few steps of solving that to be a function of y. And that would actually give you the equation for the circle, and should actually then be what the distance is from the x-axis to the outer edge of the circle, square root of 4 minus x squared. No, that's only just 1/2 of the circle, so that means that this other distance across right there is another square root of 4 minus x squared, so that means that all the way across, this right here is 2 4 minus x squareds inside of a square root across. So just based on basic circle equation knowledge that we have. So the other thing that we would need then is we would need the height of each cross section, or the height of each rectangle. And so since each cross section is going to move from 0 to some arbitrary x, we could call this distance here x. And then kind of make like a 90-degree triangle right here using this red triangle. And because of the fact that we're at a 45-degree angle of slicing, this is a 45-degree angle, and this is a 90, and this is a 45. So that means that the height right there happens to also be x. So we've got the dimensions that we need for the area of a cross-section. So the area of our cross-section is always going to be x for the height multiplied by 2 square root of 4 minus x squared for the width of each cross-section. So this right here would be the function that we want to integrate. So I did put another slide so that we could do the work for this. So I'm just copying. I'm going to move the, well, let's write it like this. So we'll have 2x square root of 4 minus x squared dx that we'll want to integrate then to find the volume of this wedge. This would be something that we'll probably need to use u substitution on because you've got something that has x right here multiplying with another thing that has x in it. So you'll want to probably let your u be equal to the function that's inside of the square root. So we'll set u to equal 4 minus x squared. That implies then that the derivative of u with respect to x would be negative 2x dx. We do have 2x dx, but we don't have the negative. So we can solve to get 2x dx alone, saying that negative du is equal to 2x dx. So then we can replace the 2x dx with negative du, and then replace the 4 minus x squared with u. So then this would be the same thing as integrating from x equals 0 to x equals 2. Your limits for u would change, but we'll keep it as 0 for 2 in terms of x, because I'll plug x back in eventually, I guess. So this is the same thing as negative integral from x equals 0 to x equals 2 of u to the 1/2 du. And then by power rule, this would be u to the 3/2 multiplied by 2/3 and negative. That will evaluate between x equals 0 and x equals 2. And so then we actually need to put the x back in. So we said u is equal to 4 minus x squared, right? So 4 minus x squared, that to the 3/2 power, and multiplied by negative 2/3, we're going to evaluate between x equals 2 and x equals 0. So if we plugged in the 2, we're just going to get 0. And then you're going to minus negative 2/3. And if you plug in the 0, negative 2/3 of just 4 to the 3/2. So that right there would be the square root of 4, which is 2 cubed, so 8. So we get minus negative 2/3 times 8, which would be positive, because the negative times a negative, 16/3. So that would be indeed what the volume is in cubic units of that wedge.